Hey folks, I got a quick uh, concept for you, and that is figuring out electric field from electric potential, aka voltage. So what we've been doing thus far is you've been finding voltage from electric field. So for instance, one of our formulas is change in voltage is negative the integral of E dot ds. Okay. And we've used that in several different ways to figure out changes in voltage. Well, what if you are trying to solve for E? Okay, how do you figure that out if you're given a voltage? So the first thing is you take the derivative of both sides of this, so you end up with dV is equal to negative E dot ds. In other words, you get rid of the integral sign. Now remember, the integral sign, it means to sum, and that's why you get a value over here. Well, now we're looking at one little part. So quick reminder, now I'm ignoring the negative sign for a second. Let's say this is E versus S. Delta V would be like if you integrate this from the beginning to this line right there, that's the area, okay? Well, what this is, dV is one little slice of that, okay? And remember, the integral sign means you add up all these slices, okay? You do your Riemann sums. Now, if we take this and we solve it for E, you get the following. E is negative dV ds, okay? And you might recognize this from before. So for instance, when we talked about force and gravity, for instance, so I'll do this off to the side here. So remember if you had, or sorry, potential energy. If you had potential energy and I said find force, well, force in the x direction was negative du dx, okay? Well, it's the same idea, okay? It's very, very similar. Now, what we're going to do is we're going to do partial derivatives because you're using a scalar. Voltage is a scalar, and you're getting a vector out of it. So a vector can have three directions, x, y, and z. So for instance, E in the x direction would be negative dV dx. Okay, and then you would do the same thing in the y and the z direction. Now, I'll mention something else. If you look in future textbooks, it's going to be written more like this. They're going to say E sub x is negative, and they kind of write it this way, dV dx. And with those little kind of different looking d things, those mean a partial derivative. It means take the derivative of the voltage function with respect to x only, x being the only variable. So, for example, let's say I gave you voltage is some weird function of space. Let's say it's 7x squared y minus 3xz cubed plus 2yz. So let's say that's your voltage, and I said, hey, find the electric field associated with that voltage, and then I'll give you a value. Like, for instance, what's the electric field at the coordinates 1, 3, 4? What's that electric field there? So it's got three dimensions, x, y, and a z, so we need to take the three partial derivatives. So E in the x direction is negative d voltage dx, which means, like, look at this first term, you pretend everything's a constant in there except for the x. So you're taking the derivative of x squared. Well, that's 2x. So you take the 2 times the 7 times the y, and you end up with 14xy. Oh, make sure it's all negative out front. And then minus, and then the next term, the derivative of x is just 1. So you got 3z cubed. And in the last term, there is no x, so it's like a constant, so you just say derivative of 0. And if you plug in your numbers, so negative 14, x was 1, y was 3, minus 3 times z over there is 4, cubed, you get 150 in the x direction. Okay, that would be newtons per coulomb or volts per meter. In this case, I'll write it as volts per meter because that's what you kind of see here, dV dx, volts per meter, right? E in the y direction, you do the same thing. You take the partial derivative of this with respect to y, so you pretend y is the only variable and everything else is a constant. So you got negative Our first term here, it's just derivative of y, which is 1, so you get 7x squared. The second term, well, there is no y in it, so it's just 0. And then plus, and the third term is, again, just y to the first, so that just becomes 1, so you get a 2z. If you plug in your numbers, you get 7 times 1 squared plus 2 times 4, and that becomes, I get negative 15 when I do that. And then e sub z should be ez by now, right? No pun intended. So e sub z is negative dv dz. Our first term, oh, got negative out front. Our first term, there is no z, so that's 0. Our second term, there's a z cubed, so that becomes 3z squared. So I could take 3 times that 3, so it's 9xz squared plus the derivative here of z is just 1, so you get your 2y. And then we plug in these values, 1, 3, 4 for x, y, and z. So we get negative, then we get negative 9 times 1 times 4 squared plus 2 times 3. And when I plug those in, I get 138. So my electric field at 1, 3, 4 is 150 I hat minus 15 J hat plus 138 K hat volts per meter. All right, so that's how you figure out electric field if you know a voltage as a function of position. There are instances when you will know that and you'll be able to figure out electric field. Now, in the previous chapters, we've talked about other ways for finding electric field. Well, here's another tool in your toolkit. So I hope that was helpful, and thank you very much.